12 seconds of powered flight. That's where it started. And in less than a single human lifetime, we left boot prints on another world. But here's the part nobody says out loud. That same technology, chemical rockets, the greatest engineering achievement in human history, is also the thing standing between us and the rest of the universe. A trip to Alpha Centauri, our nearest neighboring star, using the best rockets we have today, would take 73,000 years. That's not a rounding error. That's a civilization-ending wait. So today, we're looking at the technologies being built right now, in labs, in orbit, on drawing boards backed by billions of dollars. That could change everything. Chemical rockets work on Newton's third law. Throw something out the back fast enough, and you move forward. Elegant, simple, and brutally limited. There's a formula called the Tsiolkovsky rocket equation. Engineers call what it implies the tyranny of the rocket equation. The math is unforgiving. To go faster, you need more fuel. More fuel means more weight. More weight means more fuel. It spirals. The result? When a Falcon 9 launches to orbit, roughly 90% of its total mass at liftoff is propellant. 90%. The actual payload, the thing you're trying to deliver, is sometimes less than 2%. For a crewed Mars mission, this math becomes catastrophic. You can't slow down without more fuel. You can't come home without either bringing that fuel or making it on Mars. And for the stars, forget it. Not even close. So what comes next? Everything. Ion thrusters are already real, already flying. They use electricity to ionize a gas, usually xenon, and accelerate those ions out the back at speeds up to 20 times faster than chemical exhaust. The result is up to 10 times the fuel efficiency of a traditional rocket. The catch? The thrust is barely the weight of a sheet of paper on your hand. You cannot launch on ion thrust, but in the frictionless vacuum of space, that tiny push compounds over months into remarkable speeds. NASA's Dawn mission used ion propulsion to visit 2 separate asteroids, something chemically impossible on the same fuel budget. The future is scaling them up with nuclear power sources. And that brings us directly to the next chapter. Between 1955 and 1972, both the US and Soviet Union ran nuclear rocket programs. America's NERVA worked. It demonstrated roughly twice the efficiency of the best chemical rockets. In practical terms, a nuclear thermal rocket could cut a crewed Mars transit from 9 months to 3 or 4. The program was canceled in 1972. Budget cuts, political fear, Cold War optics. The physics, however, never went anywhere. Today, NASA and DARPA are actively funding the Draco nuclear propulsion program, targeting orbital tests this decade. And then there's the extreme version, nuclear pulse propulsion. Project Orion in the 1950s proposed detonating nuclear bombs behind a massive pusher plate to ride the shock waves. Freeman Dyson calculated it could reach Mars in weeks and nearby stars within a human lifetime. The 1963 Partial Test Ban Treaty stopped it. But engineers have never fully let go of the idea. The most expensive part of spaceflight isn't the spacecraft, it's escaping Earth's gravity. A space elevator fixes that. Anchor a cable to the equator. Terminate the other end at geostationary orbit, 35,786 kilometers up. Electric climbers ride the cable, delivering cargo to orbit for a fraction of a rocket's cost. Some estimates put it at tens of dollars per kilogram instead of thousands. The obstacle is the cable itself. It needs to be simultaneously lighter than steel and hundreds of times stronger. One material fits that description on paper: carbon nanotubes. The challenge is manufacturing them at scale and length. Japan's Obayashi Corporation has publicly targeted 2050. The materials science is advancing. This is a when, not an if. Light has no mass, but it has momentum, and you can sail on it. A solar sail spacecraft carries 0 fuel. Photons streaming from the sun push against a large reflective sail. Continuous, free, limitless thrust. Jacques Ikaros became the first successful solar sail in deep space in 2010. The Planetary Society's LightSail 2 raised its own orbit using nothing but sunlight in 2019. The limitation: sunlight weakens with distance. At Jupiter, you're getting 4% of what you'd get near Earth. This is where the electric sail takes over. Proposed by Finnish physicist Pekka Janhunen in 2006, it deploys long-charged tethers that repel the solar wind, a stream of protons that extends throughout the entire solar system and beyond. ESA is developing deployment systems now. No fuel, no limit on range. A long wire in space is more powerful than it sounds. Momentum exchange tethers rotate in orbit, physically catching spacecraft and flinging them to higher orbits or toward other planets. No propellant burned. Electrodynamic tethers run a current through a conducting cable moving through a planet's magnetic field, generating electricity, or using it to actively change orbit without fuel. NASA tested this on the tethered satellite system in the 1990s. It generated more power than predicted, so much that the tether snapped. Proof of concept, dramatically delivered. Space tethers remain one of the most underrated tools in the future propulsion toolkit. Einstein says you can't move through space faster than light. He never said space itself couldn't move faster. In 1994, physicist Miguel Alcubierre found a solution to Einstein's own equations describing a warp bubble. Space-time compressed in front of a craft, expanded behind it. The craft never exceeds local light speed. Space does the moving. The original version required exotic negative energy matter equivalent to the mass of Jupiter. In 2021, physicist Eric Lentz proposed a revised metric that may not require exotic matter at all. In 2023, DARPA-funded researchers at Applied Physics were actively modeling warp bubble dynamics. Nothing has been built, no experiment has confirmed it works. But the mathematics is real, peer-reviewed physics, not fringe science. The warp drive is not dismissed, it is simply waiting. Breakthrough Starshot is a privately funded initiative backed by over $100 million, co-announced by Stephen Hawking, proposing to do something extraordinary. Build a ground-based laser array generating 100 gigawatts of focused power and fire it at a gram scale. Spacecraft attached to a tiny reflective sail. The target velocity 20% the speed of light. At that speed, a probe reaches Alpha Centauri in approximately 20 years. Compare that to 73,000 using conventional rockets. The spacecraft is postage stamp sized. The engineering challenges are real. Building the array, surviving the beam, pointing it precisely enough across light minutes of space. But none of them violate known physics. The implications don't stop at Alpha Centauri. A laser propulsion network in Earth orbit could push larger craft to Mars in days. The ground array is fixed infrastructure. Everything launched from it benefits. This isn't a mission, it's a platform. Every technology in this video is an answer to the same question humanity has been asking since we first looked up at the night sky. How do we get there? Ion thrusters are already in orbit. Nuclear rockets are being funded by DARPA today. Space elevator materials science is advancing. Laser sail engineering is happening right now in California and Chile. These aren't dreams on a whiteboard. They are funded programs run by serious engineers making measurable progress. The universe contains more stars than grains of sand on every beach on Earth. Many of those stars have worlds. Some of those worlds may have water. Some may have life. We don't know because we haven't reached them yet. But we are building the tools that will. History doesn't belong to those who accept limits. It belongs to those who find the specific, solvable problem hiding inside what everyone called impossible. We didn't reach the moon by accepting gravity. We engineered around it, one problem at a time. The cosmos is not closed to us. We are just still building the door. So, which one of these technologies do you think will actually get us to the stars first? Is it the laser sails of Breakthrough Starshot? The nuclear pulse drives that engineers have been reluctantly shelving for 60 years? Or something we haven't even conceived of yet? Drop your answer in the comments below. I genuinely read every single one, and some of the best debates on this channel happen down there. And if this video made space feel a little more urgent, a little more real, a little more inevitable, then hit the subscribe button, because this is just the beginning. You don't want to miss the next one. And if you want to go deeper on any of the technologies covered today, leave a comment telling me which one you want a full dedicated episode on. Warp drives, nuclear propulsion, the space elevator. We can go much further into any of them. The universe isn't going anywhere, but we are.